Okay, welcome to the last tutorial of this year's QCrypt. I am Tobias Gehring from the Technical University of Denmark chairing this session, and I'd like to welcome Paolo Villaresi, who will talk about there's plenty of room out in space for QKD. As usual, you can ask questions in Slack, or you can raise your hand, and then I can unmute afterwards. Please, Paolo.
Thank you, Tobias. Good morning, good afternoon, good evening, wherever you are. It's a great pleasure for me today to introduce with this tutorial the topics, the aim, and the charm of QKD in space. I'm from the University of Padova, and as you can see, there is a COVID-compatible version of the group, subgroup in the picture, and this is an earlier version, unmasked, just to say that it's where we wanna soon go safely. Okay, so the idea of this tutorial is synthesized in this overview. First, the rationale for Space QKD, how to design it, okay, how we got it in a way to demonstrate the feasibility of it, and on next moves. Okay, so what is well, QKD at the largest scale, so QKD in space is developing from a scientific research subject in experimental quantum communication, so something fundamental at the beginning, to a phase in which a demonstrator of the different realization were provided, were proposed and demonstrated, up to a technology for supporting cybersecurity at the planetary scale and beyond. Okay, means not only on the Earth but also in space. Okay, well, we have to scale our endeavor with our planet. For instance, the 12,776 diameter object with which we live, of course. At present, Space QKD is a point-to-point technique. So it means one satellite to one place on the ground, or a satellite to another satellite, or one satellite to two locations also, okay? But the idea is that, so with a satellite, then you can cover, thanks to its orbit, okay, different locations, okay? And if you need to exchange a secure key over two locations on the ground, well, definitely the satellite's a way of doing it very effectively, because it naturally moves all over the scale that we have seen before, all over the planet. Okay. Obviously, if you have more, if you have a constellation, you may speed up the sharing of the key over to, let's say, a random spot on the ground. Okay, and this will take also some consideration later. Okay, in this sense, the satellite is meant for a networking use. Okay, so has no meaning in a single user case. Okay, for the simple reason is already in the possession of the key. Okay, but so it's intended to work in networks. Okay. And why go into space? Well, from the communication point of view, optical communication has advantages with respect to the radio frequency counterpart for the larger bandwidth of the optical versus radio frequency, thanks to the shorter wavelength. And it also enjoys lighter, smaller, and less power-hungry terminals in space. The beam has a smaller footprint on the other side, which in most cases is an advantage, and also the optical beams are less regulated in a way that you can, for instance, multiplex in wavelength. You can use the wavelength that is, say, suitable for your terminal, for your application, without have to use the deep pocket that is needed when you have to buy frequencies in the RF domain. Okay. Of course, on the contrary, you have to cope with atmospheric absorption along the line of sight. It could be rainy, cloudy, or also turbulence may affect the wavefront of the receiver, and you're suffering the background light. So, for instance, in daylight in particular, there is say a strong backlight with respect to the single quanta that you are sharing. Okay, may not be a problem in the case of classical communication, where you always have the knob of the power at the source that you can crank up within bounds, of course. But in this case, the case of QKD, as we know, we have to run at the single quanta level or close. Okay, so we're going to space with QKD. Again, the idea is that cybersecurity is a global issue. Okay, and satellite, they do have this feature that they say traveling the whole planet, not just portion of it. Okay, and even a single country, okay, need to communicate globally. For instance, for reaching its embassies or commercial branches. Okay, and if you take the case of Europe, already U27. Okay, if you take the capital for intergovernmental communication. Secure communication need to be implemented already in an area of the range of the 4,000 kilometers, okay, including islands. Okay, you have to cross the sea. And not only, mobile terminals require free space links, and as we know, ships are usually not at sight from land. Okay, so satellite again are options there, variable options there. Okay. Of course, on ground you have fibers. Okay, fibers are extremely advantageous in many cases. The propagation is characterized by an exponential loss law. Okay, that depends on the wavelength. If you pick the good one, you may enjoy a very low loss rate of the order of 0.15 decibel per kilometer. Still, that's an exponential law. Okay. On the contrary, if you have beam and far field, well, the intensity goes down with the inverse square of the distance. So there is a crucial advantage in the loss law, okay, a polynomial versus exponential, when you are considering planetary scale. Okay. And of course, when amplifier are not used, okay, as in the case of QKD. And by using the words of a paper by Chinese Academy of Science, at the end of the paper in which they demonstrated satellite QKD from Mauritius, they say that over a distance of 1,200 kilometers, even with the perfect 10 giga single photon source, ideal single photon detectors, no dark counts of the holy grail of a QKD system, transmission through a single fiber of 1,200 kilometers, due to the absorption would result in 1 bit of shifted key over 6 million years. Okay. So that's definitely that's not the way of doing it in the long scale. Okay. Okay. As we know, we need in the case of the satellite instead clear skies, turbulence and scattering from cloud, impaired optical links. Turbulence may be mitigated using adaptive optics. And about clouds and rain, okay, the coverage imports diversity on ground terminals. And maps like this are useful to design location where you can essentially diversify your ground terminals in order to, say, leverage on the fact that if you have cloud and rain on a location, it's hard, the probability of having the cloud and blockade from atmospheric problems on another location can be kept as small. Okay, this is something that is known also for classical optical communication, and it takes diversity. It takes a few more ground stations. Okay, then ground and space need to work together. Fiber links, as we know, are very pervasive, up to the fiber to the home service that we know. Okay. And they are naturally organized in hierarchy. So you have the major dorsal and then national, regional, metropolitan, local networks. Okay. By again taking an example from Chinese Academy of Science that demonstrated to complement the dorsal from Shanghai to Beijing, okay, with a satellite link for QKD, extending more than doubling the scale of this network. Okay, so it works in an integrated way. Okay. With the dorsal, or it connects isolated users, as we were saying before. Okay, and so this network need to be implemented in a way in which the satellite can be a trusted or an untrusted node. Suppose it holds all the key of your networks, and the station only have the access of their own. So suppose you want to exchange a secure key between station A and B, okay, whatever they are, on the ground or in space, okay, then the satellite first crosses over station A and exchange a key, okay, then goes over B and does the same, and then announce the XOR of the two, okay, and with that, each one of them can retrieve the other key, and for the rest of the world, it's just rubble, in the sense that no information is revealed. Okay, and with this, say point to point, you can say share then a key on the ground, wherever you are. Okay, instead of a larger scenario in a network, you may envisage to enable the satellite not only to transmit, but also to receive a qubit, as we can see the animation here we had from a project with ESA. So if you have this inter-satellite link, ISL, well, then you can envisage the way in which you can exchange keys, in particular in these blue segments in which the distance is shorter than 10,000 kilometers, where the exchange is particularly convenient in our case. And we have demonstrated that they take in this example of the constellation of Galileo satellites, so 27 satellites on 3 orbital planes. You may end up using the exchange satellite to satellite, point to point, okay, in sequence to connect all satellites in a graph that has over 4. So you have 4 different paths to connect each satellite and the network. Okay, so you see at the end we have different schemes at the end. So you can have download, upload. You may either say upload and then modulate in the satellite and transmit back, as we proposed a few years ago. You can feed from a satellite to location, or you leverage on an inter-satellite link. Okay, so several scenarios that can be realized. Obviously, this is attractive, and indeed, these type of schemes make sense for a number of motivations, and others are that space is needed as a resilience to emergency or disasters that may happen on the ground. Okay, so the possibility of still connecting QKD networks on the ground can be realized from space. Okay, the idea of say helping the classical approach to send classical large memories with keys that are fragile in harsh environments like the space is something that poses serious questions on the availability of that solution. Only combining different secure communication procedure is also an approach of good sense. Okay, so combining them, so having also the QKD combined with the known other technique for secure communication is definitely a way that encounter favor of many operators. Okay, and is sort of facilitated by the fact that a growing number of satellites they do have optical terminals for different purposes, observation of the Earth or optical communication. And so this makes the QKD payload integration easier. Okay. Well, how to say get to how to design then a satellite QKD system? Okay, we have essentially three areas of focusing. The first is the focus on the technical part. You have to choose the type of protocol, the key rate. You have to study the losses. That's dependent on the orbital type, the size of the telescope, of course, and space on the ground, the pointing and spot size, the way in which you mitigate the effect of turbulence. Okay, of course, the noise level, working at night, at day. Okay, the intrinsic noise of your system. And this will essentially gives you an effective key rate and thanks to the type of orbit that you have chosen, you have a duration of the local passage. Okay, we combining these two information at the functional level, you essentially may assess the secure bits that you can exchange with the telescope A, station A. Okay, and so you can design the things in a way that if you are interested of a given amount of key, well, that's the way in which you can get to estimate that particular value. And this enter in a network, say, consideration. So that if you have A, B, C stations, well, you then have to combine the services. So satellites need to stay in a plane that they can actually reach A, B, C, or there have to be more than one in a way that they connect in the way we just described the satellite link, for instance, in a way to say service all the points on the ground and in space. Okay. So that's the way in which you have to divide the type of study to actually realize QKD from satellites. Well, on protocols, the protocols, of course, are of the two major types: prepare, measure, and entanglement base. One considered for satellites. In this sense, you need to, for prepare, measure, you need to essentially first look at the exchange of quantum states, and then you have the error correction and private simplification, which functionally say ask for a classical communication capability that have to be dimensioned, have to be sized accordingly to the rate that you have on the quantum part. Okay, that's an important point. It can be optical, it can be radio. Okay, but it definitely need to be there when it's needed. Okay. About the choice of the type of protocol, of course, that depends on the dimensional hyperspace for the quantum states. Well, you start considering the polarization encoding span dimension 2, okay, and other type of coding like temporal modes and phase coding that are well known and used in the classical domain may allow to increase this value. Okay. At the same time, the need for checking for the eavesdropper, doing measurement in the conjugate base imposes stringent requirement on the visibility on both bases. Okay, depending on say experimental issues like the fluctuation in transmission, accurate synchronization that are needed, essentially in the quality of your signal at the end. Okay, and this say has proven quite difficult in going beyond 2. Okay, so in this sense, we may consider that in space, also thanks to the consideration we made before, we have the advantage of, say, using, for instance, multiplexing instead of increasing the dimension in a way that you are using the same, say, dimension 2 scheme at different wavelength in parallel on the same setup. As not being demonstrated yet, but it's something doable. Definitely, okay, using the same channel from space to ground. Okay, well, this is the compulsory slide on the definition of BB84, and of course, this is the say flagship of the protocols. Also, in the case of space, using these two modular unbiased bases. The efficient three-state and I think is not needed at this conference, this audience, to go into the detail of the way of actually realizing the BB84. Just reminding that the efficient three-state, the COI BB84, can be considered as the state-of-the-art in prepare and measure protocols, which you essentially encodes 3 quantum state at transmitter, you measure on 4, and use one decoy state that is needed, of course, since you are using attenuated coherent pulses, not true single photons. Okay, and the efficient part is, of course, balanced towards the key base Z. Okay, and just the X base is used to check the EVS presence. Okay, according to the realization, the practical implementation of the protocol. Okay, it's important also the consideration on the finite key effects, in the sense that in most QKD system, the operation occurs in a finite time, and satellite are actually excellent example in the sense that satellite rise and set, okay, and then it's done for the day. And so you have a finite amount of key that you can extract from that passage, okay? As we know, EVA may try to conceal action on the fluctuation that you have from passage to passage that may essentially lead Alice and Bob to overestimate the secure key that they think to extract, okay? This neglect, say, if you neglect this, you are in the so-called infinite key assumption. Well, if you say use a more careful analysis, choosing a confidence interval, you may reduce the key by taking into account this and realizing a secure key also in this case. Okay. The rate that you are available, again, useless to go into detail to this audience, but are the one that, as we know, that are strongly dependent on the probability of detecting the state and the errors that you are committing when measuring them. And with this, you have to pay a very careful attention in how you prepare the state, the quality of the detection system that you have, because this is costing in terms of rate. And for instance, if you have misaligned wave plate, your Q-bar rise and the secret key rate drops very, very rapidly, as it is derived from the Shannon entropy formula that we know here. Okay. Of course, there are also the entangle-based protocols that are very attractive in principle for being directly based on Bell's theorem. And the first and most elegant of these is the Arthur Eckert E91 protocol, that indeed guarantees the security directly from law of physics, and in a way in which, say, the source has no information about the key. So in this sense, it is an untrusted node, okay? And the elegant derivation of Arthur point out indeed that the use of the channel is based on the fact that you don't have this element of reality that were hypothesized by the APR paper, and so actually with the protocol for which you end up with this set of data, one in which the base corresponds and which they don't correspond. So this second is used to calculate violation of the Bell inequality, and the first one perfectly autocorrelated in the case of a singlet, and allows you to create a perfect anti-correlated key in the two locations that have received the entangled pair. Okay. This at the same time required the use of three bases, the determinants, while the Bennett-Brassard-Mermin 92 protocol simplify a bit the schema by using actually the same type of basis of BB84. Okay, and this is being also been demonstrated in the case of space links, and also as a key rate can be derived according to the theory that's been published, and essentially is dependent on the efficiency of both error correction and private simplification in the actual implementation. Okay. About protocols, also a continuous variable QKD from space is being considered in a paper by Daniele Paolo, Italian Space Agency, and our friends from Paris, and ourselves. We investigated the possible use of SCV protocol using Gaussian modulator in space, and the receiver in which you have a free-running local oscillator and a reference symbol for phase recovery. And the technique involves the use of subdivision in time slot for the, say, analysis of the noise in the detection, and also the use of an interleaved beam to mitigate the effect of transmission fluctuation. Okay, in this case, by using carefully this two ideas. Positive secure key rate is being envisaged for a satellite in low orbit. And by the way, the feasibility of a continuous variable was demonstrated in terms of detection at the quantum limit, okay, even from satellite in geostationary orbit, so the highest possible altitude in the case orbit and terminals by our colleague and friends in Germany. And this is actually something that has demonstrated say quantum communication from GEO using CV. Okay, that is also very, very attractive. Okay. Well, we were saying on how to say realize the key. So how much key can we get on clock rate at the end? Okay, clock rate means that the use of a channel that is possible. The secure key rate scale, of course, with the number of users per channel. Okay, so the secure key rate at the end is the probability of doing a secure bit, okay, per user of channel. You multiply by the many uses that you have done at a unit time, and you get the secure key rate. Okay, in that particular realization. So higher rate are both wishes and fear. Indeed, it improves a higher value. It improves the key rate, but at the same time, okay, the discrimination of Alice state as measured at Bob side, okay, requires corresponding temporal resolution, orbital determination, okay, and so this is something that is more and more involved experimentally, okay, to realize that, and at the same time, if you increase the rate, it means also that you increase your demand in power, the state generator, the computing capacity, the memory you have to use on board and on ground, okay, as well as the data exchange, okay. So presently, thanks to the demonstration, we'll see suitable values in the range of the 100 megahertz range, and more to come, okay, essentially with demonstration. Experimentally, I can show you, we have a limit in the sense that we are actually in the action of discriminating single photon coming from objects that are flying like like satellites, because they are like satellites in the dark sky, okay, and so the resolution with which you may think to set your detection scheme is bounded by several experimental parameters. And we've done an experiment in which we say analyzing the return from single photons from a satellite at 7,000 kilometers, and we've seen that the width of the curve was about a quarter of a nanosecond. Okay, that sets more or less the limit at the moment for this time resolution. Okay. So send space from space, where from? Okay, we know that satellites are designed and launched to stay in different type of orbits, low Earth orbits, so lower than 2,000 kilometers, medium Earth orbits between LEO and the geostationary. Of course, you have different feature of the different types. Okay, the low orbit, they have rapid passages, so you have a coverage of the planet that you can realize more rapidly than with others. Okay, at the same time, the passages are quite short, a few minutes, up to 10 minutes. Okay, the medium Earth orbits are from ground seen as slower. Okay, and for instance, the GNSS for gravitation navigation positioning services like Galileo, GLONASS, GPS, class of satellite there. It's about 20,000 kilometers. And the geostationary satellites appear to stay always fixed in a position, but they are very, very far away, okay, about 36,000 kilometers, and which means that the losses also in the case of the quadratic scaling indeed are very relevant. Okay, then there are also other types of of trajectory that are not orbiting, like in the case in which you would like to go to another planet or visit other part of this space. I would like also to mention the fact that the growing number of satellites is indeed posing issues, for instance, to astronomers, okay, because satellites at dawn and dusk, they are scattering light towards the ground, and they can impair a certain class of observation of the sky. We know, of course, that it's nice to see, for instance, the passage of ISS, something like that, and this is helped by many apps, okay, and well, you have a few passages per week, okay, if we are talking of a few satellites, but Francia, for communication purposes, to send in space satellite at the rate of tens of thousands, okay, and you may end up that the observations of the astronomers are like the one on the right part of the figure, so marred by a continuous passage of bright satellites, much brighter than the object that they are looking at. Okay, and so low scattering profiles and absorbing material are actually needed in this sense. Okay, so the first question on how to do it is downlink or uplink. Well, we know as the atmospheric condition is impeding the wavefront close to the ground, usually you like to have this degradation at the end of the path so that you have most of the propagation in vacuum, okay? And so the downlink is preferred unless there are specific motivation for doing the contrary, like you like to change the type of source or say connected with other on the ground, things like that. So there are ways also in which an uplink can necessary. How you devise the losses now that you have chosen the way? Well, you essentially have three factors. Okay, the clipping of the receiver signal by your terminal. You possess a telescope to look at the signal from the satellite, but this signal is spread over an area usually much larger than your telescope, and so you have a geometrical clipping. Okay, and then there is an issue about the field of view. Okay, you have to aim accurately at the satellite. If you are not pointing exactly, you may lose some signal. And of course, you have the atmospheric transmission that attenuate the signal as well. Okay, if you do some modeling, I don't want to go too much into detail in the formulas, but just to convey the intuition, if you take three cases, for instance, a telescope in space whose size is 10 centimeters, 30 centimeters, or a meter, okay? You have this curve about the size of the spot on the ground for different wavelengths that you can use. Of course, diffraction scale with the wavelength, so the area is squared about that. So 850, 1064, 1550, you can recognize usual laser wavelength for also enjoying the use of the sources according to the technology. Can show you that for the small telescope, you are in the range of a few tens of a meter for a LEO orbit, so about 2,000 kilometers, 3,000 kilometers, several tens of meters of the spot diameter. While, of course, if you have the giant 1 meter telescope, well, you can go as low as so a few meters. Okay, of course, a 1 meter telescope is a giant, and not only to build it to astronomical quality, to launch it, but also to point it accurately. Okay, and so this is something that can be considered, for instance, only for the big geostationary telescope or things like that. When you consider the clipping, so when you go on ground with, for instance, a 0.5 meter telescope, okay, then you can calculate the losses, okay, from the table before, and you see that the losses for LEO satellites can stay in the range between 30 and 40 dB in the case of the 10 centimeter and 20, 30 in the case of the 70, 30 meter. leaving alone the 1 meter case, which of course is much more, powerful in the sense to concentrate your photons just in your telescope very efficiently. Okay, when you are plugging the losses into the key rate for the 100 megahertz rate, we can see that still it is for single use of the channel. You can see that for LEO cases, the key rate are in the range of 10⁻⁵, 10⁻⁴, okay, per use of the channel. Then you multiply this by the number of use of the channel per second, you get skew bit per second that you can obtain. Or if you look in the other way, if you want to obtain at the end a secure key of the size of, for instance, of 1,000 bits, okay, in this paper we analyzed the different cases of finite key security, different level also of the security. Well, the idea is that if your system is providing you, for instance, 4%, then you know that you have to realize your satellite system, transmitter, receiver, and pointing, things like that, in a way that you have to receive about 20,000 qubit in order to obtain the result that you are looking for. Okay. Besides this, there is the transmission issue, so the absorption that is well independent, and using load transmit and the Python here I've calculated in the case of different inclinations, so vertical, 60 or 80 degree, that is showing that you have good region and bad region, okay, and you have to stay away from these holes that are due, of course, to atomic and molecular absorption of the atmosphere. Okay. On top of this, you have turbulence. If you are looking even to a fair bright star like Vega, with a big telescope like this one, Matera 1.5 meter telescope of Italian Space Agency. It is big. You can see in comparison with the Francesco and Luca in the image. Well, what you get is that the image is wandering. So, or you have a large detector that say account for these movements, or you have the way in which you can say measure the fluctuation and in real time correct the wavefront in order to inject in a single mode. On this, we have several advantages with respect to the same use that is done by the astronomers, in the sense that you can say essentially look just to a small field. Okay, you just need to look at the satellite and not to an image. And you can also use the beacon that is associated with the satellite with the quantum signal. It is much more effective than, for instance, using the simulated star. It is noticed that if you are using a small beam, okay, in this case, for instance, we had 120 millimeter, and with d over r naught, with the radius of 3, okay, just tip tilt is enough to achieve a good coupling losses. And if you are not correcting the motion of the spot on the focal plane, you get the red clouds. If you just use a tip and tilt, so you measure the deviation and you correct it just by inclining a moving mirror, you go to the tiny blue part, okay, that allows you to have a suitable injection into even a single mode fiber, which is very, very relevant. So after this part on the design, how we got to demonstrate the Space QKD. Well, we have essentially 3 phases. The early 2000 was of proposal and modeling. Later came feasibility demonstration. And I would say since 2017 on, we have investments on the development of Space QKD in connection with the ground. Okay. Very rapidly going through the demonstration, I would like to recall this work of the UK friends and colleague that already in 2002 envisaged a kilobit of secure key using 1 meter telescope. There were also the idea of realizing entanglement distribution, and with that using also fundamental properties of the entanglement for securing QKD, securing the communication from Vienna. We approached the issue on the experimental part in Matera by doing studies on reconstruction of the orbit and envisaging a way to correct the different, say, non-idealities in polarization. And in China, they addressed the issue of sharing and say, entangled states through atmosphere, demonstrating the doability of this so that also, say, the Bell test can be done in free space in schemes that are compatible with space, okay? Experimentally, lately, we came with a demonstration of the single photon exchange with an orbiter, using the idea of having a beam that is sending up in space, and just a fraction is re-emitted with a mu that is 0.4 in this case, so you are at the single photon level. And at the time, the paper appeared in 2008, we were able to actually identify that over the noise. And this say, made the news that quantum communication with satellite might soon be feasible. Okay, this type of demonstration of the exchange of single photon was then extended, still working in Matera, to 7,000 kilometers and then to 20,000 kilometers to this strategic altitude of the GNSS satellites. Okay, then there was the issue of coding in the photons. A protocol like the BB84, okay, this was done using polarization degree of freedom, and in particular, we're using retroreflectors on satellites. This time using satellite with metallic coating on the corner cubes in a way to preserve the polarization state. Okay, this way you can say design things in a way that they are single photon coming back and polarized states. Okay. We were using an interleaved intense pulse for ranging, okay? And with that, in 2014, we were able to demonstrate actually the force state needed for BB84 correctly detected on ground, first from this satellite LARETS, okay, with a return rate of the order of 100 click per second, okay? And later with other satellites in a way to demonstrate that you can actually keep the Q-bar at the value that is compatible with the application of the protocol and stable for an extended amount of time. Obviously, we need to check the rate in a way to be sure to be at the single photon level for all the passages. This was done using radar equation that is common in the case of satellite laser ranging. Okay, so this was actually the first demonstration of the Q-bar, the doability. This made the highlight of the year 2015. And after that came a demonstration with actual missions, major missions where we dedicated satellites came in Asia, and feasibility study and progress in orbit validation were elsewhere. So temporarily first to mention the Japanese satellite, the SOTA, that had classical communication as well as sources for polarized photon on board, okay, that was detected in Japan and Korea, and also in France, that allowed to study also the correction of the state on the ground using altitude optics, and also assess the value of the Q-bar in the case of the polarized sources compatible with the protocols at the time. And then came the Misius satellite of the Chinese Academy of Science from actually a formidable team that was indeed a multi-purpose mission, providing us excellent example of many of the possibilities for space QKD. It was launched in 2016. We have a few images of the satellite, and it was not just a satellite, but initially 5 ground stations that they developed to demonstrate the different protocols with the satellites, and indeed it was a very important effort, also financially. The satellite has a say complex way of pointing and to share time with the ground, setting also as a reference in terms of tracking error, the order of the microradian, that is actually a very advanced value, thanks to a splitting of the course and fine pointing on board of the satellite on ground. Okay. With MISUS, it was possible to demonstrate the quantum key distribution, okay, from the satellite. We see the passage there. They implemented the QCrypt 84, and this allowed it to demonstrate experimentally with an active source rate of the order of 10,000 kilobits per second, okay, and not only with the location in China, but with that they actually demonstrate the protocol that I've described before, by going in another location, another continent, and doing with safety key rate from 3 to 9 kilobits per second, an exchange with the terminal in Austria that allows, for instance, a video conference secured with the S128, changing the key every second, and also the encrypting of file and images. Satellite was also equipped with a state analyzer. So by sending state from ground, they were able to implement a teleportation experiment, which the already collapsed photon was directed to the satellite up to 1,400 kilometers in space, and they successfully demonstrated teleportation of all 6 input states needed for the generic teleportation protocol, okay, with the necessary fidelity. Okay. Satellite is also equipped with an entangled source, and it has 2 telescopes, different sizes, 200 and 300 millimeter, that was used to distribute entanglement and to measure the Bell parameter at the unprecedented scale of 1,200 kilometer, okay, confirming local feature of entanglement in this scale from space. This entangled source was later used in the application also of the BBM92 protocols, again, over 2 locations in China, okay, Nanshan and Delinga, separated by about 1,200 kilometers. Okay, in this case, they have a rate that was, of course, say, on the fraction of the bit per second level because of the losses of the 2 channels in parallel. Of course, you are paying this price of, say, having lower rate because you have 2 beams, but this was demonstrated of untrusted node QKD. Okay. As I said at the beginning, with MISUS, they were able to extend the 2,000 kilometer dorsal to more than double distance, double scale, in this, say, continental network, the size of 4,600 kilometers, okay, in which they are at the level in which QKD system are indeed a basic layer in a communication stack that is already at the application layer for many different uses in practice. Okay, so MISUS is still in orbit, so I'm looking forward to new result from Chinese Academy of Science. I would like to mention also the effort in Singapore, where they demonstrated on a totally different scale on CubeSat the use of, say, very, say, reduced powers, mass, size for actually realizing sources, like in the case of Spooky 1, a CubeSat in LEO that has successfully demonstrated the use of an entangled source in orbit in LEO with actually very, very limited mass, and also with a price that is much more say compact with respect to, of course, the scale of MISUS. Okay, this idea of CubeSat project taking seriously by many countries. And for instance, well, the CubeSat actually are expanding because they are leveraging on more and more advanced components suitable for good pointing, say sources that are compact, more power available. And for this reason, many countries, also in Europe, they are pursuing a project on quantum communication using CubeSat, and I'm listing there a few of the project about that. Okay. More generally, in Europe, the idea of quantum communication is taken very seriously at the level that they announced the future is quantum. It couldn't be more more bold than this. Okay, and indeed there are ongoing studies on the architecture at the level of the continent, of quantum communication infrastructure. The space segment is in the hand of the European Space Agency, and there are ongoing studies on the different specific application, the technology, the idea of demonstrating in orbit, and of course the link on the ground part. In terms of demonstrating QKD, there is this major test bed project whose name is OpenQKD, that embrace more than about 40 partners, and has many user cases featuring different particular application of QKD, going from e-government to financial service to healthcare. Okay, this is instrumental for say stimulating the application in terms of this also action that has been signed by all the member states of creating this quantum communication infrastructure. The idea is that you can have also intermodal QKD, means that from a free space you get into fiber, and from fiber you get into a local node. We are partner of this project just for also for this part in which you can see here in a network deployed in Padova that you can say change the mode of this. Okay, in terms of a ground station for nodal points, you need large telescope for a rate like the 1.5 meter telescope in Matera or 1 meter in Tenerife. Okay, while for single users, the class of 40 centimeter, half a meter is possibly the one more convenient. Okay, and of course for ground-to-ground space links, you just need a few centimeter optics. But the idea of the 40 centimeter is something that the present technology can be installed in existing building, like in the example here at the University of Padua in downtown. Okay, the telescope are good for observation, for also tracking LEOs, something like that. They are quite compact, so they are, say, possibly very convenient tool for a distributed ground network of receiver from satellites. Okay, indeed. By looking at the opportunities, okay, as many continents, they have announced action opportunities, the development of multiple ground networks is actually ongoing. Okay, satellite for QKD demonstration, first governmental and then commercial, are under realization. Many continents, besides China, that already have done it. The ground station need to be deployed in a way that they have to, say, connect a ground network and give the redundancy and provide, say, the use to isolated, say, interested nodes. So they need to be deployed. So there is an effort that is needed there. A new space economy may develop from that. Secure communication will use QKD, as the announcements are made in many countries, including USA, and as you can see, there is the bracket quantum and gov, whose result is possibly in normalized dollars, and this is actually an opportunity for application and new schemes. Okay, so here to say that space QKD is actually something which now we have chances of doing a lot of things. Okay, of course there is a standardization issue. Standardization of QKD is ongoing. I just pointed the page of ETSI for Europe. but as a space party is in development phase, this will lead, once this has been demonstrated, to standards that help global operation. Okay, where to go? For instance, one thing is the daylight operation, as was pointed out in a paper by Cass. As the satellite, for instance, has a higher altitude, you have more and more fraction in the shadow, okay? And you then consider to use a different wavelength where you have lower background. So 1550 comes at hand as a wavelength. For instance, we realized that PIC, an integrated photonic circuit, at this wavelength to demonstrate in daylight. We did the experiment on the ground so far, showing that it's not only doable in day, but also from these very small sources that are, of course, in line with the idea of having an efficient and compact source, even possibly to multiplex in wavelength in a way to increase the rate from space. In terms of, say, directions, well, the QKD implementation in space will also enable a number of fundamental study, new science possible. This graph contains many issues taken from a recent review. And just to bring you a few examples, again, from Chinese Academy of Science, we have a result that is an element, for instance, able to say compute an hypothesis on a possible decorrelation that may occur in entangled pairs once one of the two photons is crossing the space, changing the gravitational potential. Okay, the hypothesized the correlation that has been initially proposed in the event formalism was actually ruled out. Okay, we were talking of polarization so far, but there's more. If you consider the quantum interference from that you can have from superposition and physics, this can be realized using different degree of freedom. For instance, if you take temporal modes, you can create a time beam, okay, and you can think of having them to propagate in space and to be detected. And at the end, this can be a way in which you can expand in space in QKD. And we did an experiment just doing a time beam that is being sent to a satellite and detected back and measured with an interferometer that was used in a way that you have a signal that is going out in both possible paths, short and long, and return from short and long. And if the photon has chosen long, it appears with the one single peak in the late position, the short appear at the early position, and you have two interferent other opportunities in which you get the photon out from the short and back from the long, and out from the long and back from the short. Okay. In this case, you have an interferent part. This interference depends on a phase that is dependent on the velocity, okay? Because the satellite is moving, is approaching to where you are going away from you during its motion with respect to the ground station. And so when it reflects the light approaching you, well, the reflection of the second part of the time beam is slightly closer to you, okay? And this causes the phase, which can be modeled, okay? And if you consider the probability of having a click at the central peak, so having constructive of destructive interference, it is something that modulate with respect to this kinematic phase, we call. Okay, we've done the experiment, and you can see that actually we were able to see the constructive and destructive interference. Okay, and this attests the interference, this single photon level over passages of 2,000 of the distances of 2,500 kilometers, with the visibility that actually suitable for use also of temporal modes in the case of satellite quantum communication. So temporal modes and polarization. two opportunities, why not to combine them, okay? And we indeed look at the idea of combining them by doing a fundamental test, okay? We know in quantum physics we have wave-particle duality, and this is indeed, say, a consequence of the very fundaments of the reasoning on the nature of quantum world, okay? This was brought to an extreme by John Wheeler with the idea of the delayed choice experiment. And we actually, in which actually you decide which type of measurement to measure the particle or the wave-like behavior on a quantum object, deciding which measurement only after the moment in which the particle itself has entered in the experimental apparatus. So this type of experiment we thought to bring in space by combining these two degrees of freedom. Polarization was suitable to actually decide to be used as a switch, okay, to measure the particle-like or the wave-like behavior, and the kinematic phase in the temporal mode was, say, the one that will allow us to see the wave-like behavior, the modulation in the phase. And so if you, say, realign in time, you actually have interference of the two paths, and so you are sensible to the kinematic phase. And if you split them in two, you have a peak corresponds to the long and a peak corresponds to the short path, so which way path that is a particle behavior. And by choosing this after the reflection of the satellite, of the path from the satellite, allow us to implement the Wheeler choice. Okay, this was indeed realized, and the interference that you have seen allow us to determine with clear statistical evidence the validity of the quantum mechanical interpretation in wave-particle duality. Okay, this was as for the Wheeler boys. Okay, and so in conclusion, okay. In conclusion, the path to space QKD is clearly open and viable, okay, has been demonstrated in a number of protocols already. Okay, the growth and spreading of it depends on the effective application of the demonstrator and concrete integration with the ground net. Okay, so in order to actually see it growing, you need to be concrete in doing it, to do it fast with in-orbit validation, and to be, say, able to cope with the need of the ground network. Okay, it is also the occasion to look ahead, to use new paradigm, to conceive new type of views of this. Okay, and the idea is definitely very attractive, very charming, because at the end, okay, after all, say, we are dealing here with the most fundamental communication level. You are exchanging quantum states that was ever conceived, and you are doing it at the largest possible scale. So definitely there's plenty of room here for quantum communication and QKD in space. Okay. With this, I would like to thank you for your attention. I would like to say hi also on behalf of Quantum Future Group, city actual member, and Paolo here for space, and Current G part, and thank you for your attention.
Thank you very much, Paolo, for this beautiful tutorial. So if you have any questions, raise your hand or write it in Slack. I can see in Slack that Neil Kundu has a question. He's asking, how is the free space path loss in the satellite ground channel mitigated, because it's rather high?
So the losses is something you have to put in the budget, okay, in the sense that the only way in which you afford to lose some photon is to repeat the action of sending them many times per second, okay? And the combination of the rate and the use of the channel have to give you a number greater than 1, okay, essentially, okay? So given the design of a satellite and of the ground station that eventually allows you to obtain in a particular say condition of also of the meteor or things like that, say 10 to the minus 4 as probability of having a secret bit produced of the channel. Well, if you are running at 100 megahertz and that was 10 to the minus 4, then you have 10,000 secure bit per second. Okay.
Maybe I can add on this. Do you do any? Do you trust any parts of the loss in the security analysis, or do you do this as we basically do it on ground?
Well, in the demonstration that I've described, we don't have trusted part of the channel. Okay, so you discard all the events at Alice's side that were not detected by Bob, and the application of the protocol is considered to be by the book, essentially. Okay, so as if it were on fibers. Okay, of course there are approaches that are considering different altitude that are considered safe or things like that. And this is a topic in evolution, let's say, that could bring different protocols.
Neil, I can see you have more questions, and maybe you can ask them yourself.
Yeah, so basically I want to know, is there any experiment of continuous variable QKD in satellite? And which is better for satellite channels, the discrete variable or the continuous variable?
Well, I've mentioned this test, fundamental test on the noise analysis that was done in 2017. Okay, and that definitely has led to an idea of working on the source. That particular case was using an extraordinary operation mode. Okay, but that can be say transformed in a way that could work properly in a CV protocol. Okay, that's ongoing, and I don't know if I published the result there at the moment.
Are there any other questions?
Yeah, so I have one more. So you have talked about satellite QKD. So can the same principle be used for terrestrial, like using optical frequencies, like for mobile devices using the Li-Fi access points? Like can this be extended for our mobile devices also? So short range QKD.
I'm afraid I had some problem with the line. And may I ask you to repeat your question? Sorry.
Yeah, so my question is that since this long distance is demonstrated in satellite QKD, so can this same principle be used for terrestrial mobile devices? Like in our mobile phones, can we expect to have QKD in the near future?
Okay. The idea of say developing a technology that say connect mobile things is definitely there, in the sense that, as we say, for instance, also ships, also planes, also low altitude platforms of interest for secure communication, for simple reason, like for instance, that you are generating information, contents that you would like to transmit safely, or you would like to secure the command that you are sending to the device, to the platform. Okay, not because the commands are secret. Okay, it could be just turn left or right, but you would like to be the one that is actually telling the command to the device. Okay, and of course this may happen to distances that in general are shorter, and for this reason they are less demanding than in the case of satellite. Okay, also the environment in space, you have to cope with a harsh environment in terms of radiation in terms of, well, vacuum, vibration at launch, things like that. While in the case, for instance, of a drone or a plane, definitely you have to be compliant with the specification of your environment, but this is definitely more relaxed than in the case of satellite. So which means that definitely, yes, you may learn from satellite links and try to expand to shorter links, distances, and things like that. It's probably easier and cheaper. Okay. About the mobile phone, well, indeed, this has to do with more the terrestrial use. First, the question is, do we actually need now to have a phone with QKD? In many cases, you may answer yes. Okay, so there are ways in which you may empower the phone with a QKD exchange somewhere else, okay, in a secure way connected with the phone, or you can empower the phone itself with an actual transmitter or receiver. Okay, probably it's best to keep it with the transmitter. And there are ideas and projects to actually miniaturize the transmitter to size and say the amount of power and computing that are compatible to a phone. Okay, so although this is not a direct spin out of the satellite to ground communication, I'm definitely convinced that this may be realized in the near future.
Tunmise, do you have a question?
Yes, indeed. Thank you very much. Thanks very much, Paolo. Very nice talk. My question is about wavelength selection, which is not necessarily trivial. So my question is, what would you say are the most important factors for wavelength selection in free space or satellite QKD, perhaps?
Good question, thank you. The doability of the whole system depends on many parts: the sources, modulators, channel, so the diffraction, transmission, the gathering, and the detection. Okay, and you have, definitely relevant aspects on all these things, from the availability of sources to the availability of detectors, suitability of the wavelength for being transmitted in air. Okay, so for diffraction, the shorter wavelength is the better, up to the point in which you have Rayleigh scattering. Okay, because after all, the sky is blue, and beyond that, you can even get totally absorbed. You may go further and get to the X-rays, very good for low diffraction, quite hard to detect, and as well as to generate and modulate. Okay, so well, for being practical, you have the 800 nanometer range in which you have good sources, good detectors, but also quite a strong background. And instead 1550, where still you may have good sources, the detectors are there, but they are more involved, and you enjoy essentially a lower background level. Okay, to say something, just to mention a few of the major aspects. Okay, of course there are many. Okay, so indeed the tail analysis in which in different countries we are working on at the moment are to find the good solution, the best compromise for a different application that you may consider.
Great, thank you.
Are there any other questions? Otherwise, maybe I can ask one last one. So in the industry session, we learned that Rupert Özin claimed that satellite QKD might be economical for distances as short as 200 kilometers. Bruno Hattner believed it was more 1,000 kilometers, and Andrew Shields more intercontinental. So I would like to hear your opinion about that, Paolo.
Well, as I mentioned, if you consider the evolution of the small payloads for CubeSat, okay, you actually can realize that the evolution of technology at this, say, low-cost level indeed provided tools for doing things that just a few years ago were doable only with major satellites with a major price tag, okay? So a statement like this, I think, they probably are based on the reference to one particular technology or the other, okay? Definitely, if you are considering a 24-hour, 24/7 type of service from geostationary satellites, the price tag still is the sort of traditional one, because you have to launch something that is actually capable of staying in very harsh condition for decades and cope with a very, say, large telescope with the ultra precise pointing. Okay, that's something that is definitely expensive. Okay, you may also consider the other approach in having something realized at the antipode, okay, this reasoning, and would probably make things easier. There is also the ground part, okay? It's not just a satellite. As you may have realized, okay, one satellite is actually aimed to feed many ground stations, okay? And the ground station themselves need to be, say, versatile, also affordable, okay? So not like the big one that I've shown you, okay, but more like the urban one of whose photo you have seen, okay, that you may say locate on your own roof, essentially, okay. The development of this technology is also critical. It means it takes know-how, it takes the use of different technological parts and things like that. So experience for doing that. And also this may be a game changer, okay? And this is essentially also what I was underlying. I mean, there is an opportunity now, but we actually need to be fast in demonstrating it and effective in the solution. They have to work to be actually of help on the ground part in close times, and this will allow an actually flowering of the space segment as well.
Thank you, Paolo.
No one have asked what it looks like, okay? And this is the reason why I put this photograph and also the one in the back, okay? What you have is this beacon beam, the single photon you don't see, but the beacon beam, yes, they are going in the dark sky, and it is amazing, okay? So this is also one of the basic reasons actually for scientists at the end, since beside the interest, that the economical, say, motivation, thing like that, it is also the fact that it is very cool doing these type of things that's motivating. Okay.
Thanks, Paolo. I think we're at the end of the session. So thank you, Paolo, again for this
been a pleasure.
nice tutorial.
Thank you.
And you can meet Paolo on the Meet Anywhere platform. And thank you very much again. Bye-bye.
All the best from Padua.